Okay, so I think today we're going to kind of proceed with our lecture on the generalized Lasso problem cases. And then if there's time at the end, I'd like to go over some of the kind of more problematic questions on the midterm, just to make sure we understand what the common mistakes were. If we don't have time to go through that, or if we end up not covering a question that you were confused about, please make sure to go through the solutions to the midterm. If they're not already on Piazza, then they will be today. We have them finished. So make sure to go through the solutions to the midterm. I do that in any case, whether or not you did well or didn't do as well as you'd hoped. Make sure that you understand those solutions. It's definitely very important. The midterm was I think it was on the longer side. That was the consensus. The questions, I think, were at a good level, but I think people found it a little bit long. And if you look at Piazza, you can see a histogram of the scores. So it's you can see that it's pretty spread, and you can also see that the majority of the class found it long. We can't say off the top of our heads now what it means to get a 25 on the midterm or what it means to get a 20 or a 40 or whatever. What we can say is that the mid-semester grades you received, so the semester, you got your kind of half mid-semester grades already, those are intentionally harsh to try to motivate you to do better. So those aren't necessarily reflective of your final grade. We put those a little bit harsher than what you'll see for your final grade on purpose to try to motivate you to do better. So nobody should be dropping the course without talking to me. If you're worried you're not doing well, don't drop the course, just come talk to me, and no one's going to fail unexpectedly. Trust me, we don't do that in this course. Don't drop the course, just come talk to me if you have any concerns. Other than that, just work hard on homework 5 in the little test, and you should be in good shape. Other questions about the midterm, besides questions about the individual problems? Do you guys have any concerns? Okay. Like I said, just come talk to me if you have any concerns. And if you have trouble, following one of the solutions on the midterm that's posted, come see me or the TAs. We definitely want to make sure you guys understand those. So last time we covered about half of this lecture on a case study of generalized Lasso problems. We're trying to see how to put together a lot of the algorithms we've seen so far in various instances of the generalized Lasso. Try to give you an intuition for how you might go about doing this in your own research when you come across a problem that you want to solve. So, just keep in your mind, we're not going to go through this again, keep in your mind the various problem cases that were interesting, like if the penalty matrix in the generalized Lasso encoded pairwise differences that corresponded to what we called the fused Lasso in one dimension. We could also do higher order polynomial differences, and that corresponded to what we called trend filtering in one dimension. And then we also saw kind of a more broad application of this idea, which is similar idea, but over graphs. So we call that the fused Lasso over graphs. And I also claim that you could do trend filtering over graphs too, although we didn't talk about it in this lecture. And the last case we went through was when this penalty matrix D is big and dense, and we had some motivation for that as well. So all these cases we wanted to think about in terms of algorithms. And last time where we got was that we said for the linear trend filtering problem, right? So if D is this particular difference operator, take second order differences in one dimension, and the loss was either Gaussian loss or a logistic loss, or it could be actually one of a few other losses along those lines. Then we saw that when we stepped through each algorithm, it looked like the best one to use was the primal dual interior point method. On the dual, actually. So the best thing to do was to derive the dual of the generalized Lasso problem, which we can see here. This is the dual. To look at the dual and apply an interior point method, like the Berry method or the primal dual interior point method, to the dual. And that was because we could take these constraints, this box constraint, and write it as a set of linear constraints. And we saw that the difficulty in these interior point methods reduced to solving linear systems in the Hessian. And for this particular class of problems where the penalty operator looks like this, those linear systems were banded. And so we were in luck. We did very well in that case. And the other algorithms all struggled. The other algorithms we considered applying, like the primal subgradient approach, was very slow. It's very slow to converge. Primal proximal gradient didn't make sense because the prox operator we didn't know how to solve. Dual proximal gradient had efficient iterations, but it was very slow to converge because of the poor conditioning of D. And the interior point method, it wasn't nearly as affected by the conditioning, right? Because we know that, for example, anything based on Newton's method is affine invariant. And the linear systems were very easy to solve because of the banded structure, so we had kind of all the right properties in this case to apply the interior point method. So I went through that very fast, but that was basically what we covered last time. Any questions about that before we move on? Because it's kind of important that we understand the strengths and weaknesses in this case before we go. Okay. So this was an example we saw in the first lecture, just revisited now in detail, right? Because we actually studied the kind of individual components of each algorithm. The dual interior point method, I actually ran the barrier method in this example on the dual of the linear trend filtering problem with the Gaussian loss. And after 20 iterations, this is the iterate that I found. And with 10,000 iterations of proximal gradient in the dual, this is what I got. And we know that this is not the right structure at the solution. The solution should be piecewise linear. The reason this happens is because, well, it's two reasons. The first is that first-order methods, like proximal gradient, are slow to converge to solutions of high accuracy. And the second reason is that in this case, it's especially slow because of the very poor conditioning of D. We looked at the condition numbers of D, and they were enormous. They were on the order of 10 to the 10 for a problem of this size. Okay, so let's go to now a slightly different example, which is the graph fused lasso. Right? Remember, we're looking at the difference operator over a graph, rather than say some differences over a line, which is the univariate setting. It's really the same story, as long as the losses are what they were before, like a Gaussian loss or a logistic loss. The primal subgradient method is very slow to converge, right? So it's not really a viable candidate if we want solutions of even kind of moderate accuracy. The primal proximal gradient approach is not possible because we can't evaluate the prox operator, right? The prox operator reduced to this prox, which was say prox of beta at the level t is equal to the argument over all z of 1 over 2t times beta minus c squared plus, let's just say dz. Right? And this itself is a hard problem. In fact, this itself is the problem we want to solve if the loss is Gaussian, when d is something like a difference operator. This is not a tractable prox in general. Deriving the dual, let's just remind ourselves, what do we need for the dual? We needed a few things just to get to the dual. We needed the conjugate loss to be something that we can write down. Right? So depending on what the loss is, we may not actually have an expression for its conjugate, but in the case of say these two losses that we've been considering, the Gaussian logistic losses, here are their conjugates. Right? So if the loss is either this Gaussian loss or this logistic loss, we have their conjugates, so we can go to the dual. So that's one property that we know we can deal with. Another is we need to be able to solve for a primal solution in terms of a dual solution. So we need, it looked like the gradient of our loss function at beta plus d transpose u. This has to be solvable. in beta in order to use the dual approach, because we're going to find the optimal dual solution with an algorithm on the dual. But what we really want is an optimal primal solution, and from the KKT conditions, we saw that we had to actually be able to solve this in order to characterize the primal in terms of the dual. That's another property that we need. And again, for these two losses, we saw we could do that. This emitted closed form expressions for beta in terms of U. Okay, so that's just a recap of what we need for any dual algorithm, just to go to the dual. Okay, so in this case, we have these two properties, as we saw, so we can think about applying dual methods and then getting a primal solution eventually from this. And the dual proximal gradient approach is very cheap to iterate, just like last time, because if you look back at the dual, right, say here was the dual problem. If we want proximal gradient on this, then the gradient should be very easy to calculate here based on the chain rule. And the prox operator is just projection onto a box, which is very simple. Okay, so that was something that's nice about dual proximal gradients. However, it's really the same story as with the trend filtering case. It's very slow to converge. So if we want a solution with even moderate accuracy in this problem, we're doing the fuse loss over a graph, it's hard to use proximal gradient in the dual. An interior point method is going to have essentially the same strengths in this problem as it had before. So for the fuse lasso over a graph, the answer is really still to use the interior point method on the dual. What are the linear systems that the interior point method would visit when it's trying to solve the dual? It would have to solve linear systems in the Hessian of the dual kind of barrier smoothed criterion. And to go back to what that was, right, the criterion looks like T times F star of minus D transpose U plus phi of U, where this is the barrier function that incorporated the box constraints. If you look at the Hessian of this, then it's going to look something like D, the Hessian of the conjugate loss, evaluated at minus D transpose U times D transpose, plus the Hessian of the barrier function, just to remind you. So we have to solve linear systems in this in order to apply an interior point method on the dual. For these particular losses we're considering, the Gaussian and logistic losses, for example, this is a diagonal matrix. This is always diagonal. If you looked at the nature of the constraints, they were just component-wise constraints on U. So the barrier function is always diagonal. And these are very structured. So in the case of linear trend filtering, they were banded. In the case of the fuse lasso over a graph, they're no longer banded, but they're very structured. Remember, for the fuse lasso over a graph, these D matrices looked like they had just a -1 and a 1 in each row in different spots, right? Where the -1s and the 1s corresponded to edges in the graph. So if you've taken, say, a class on graph theory, maybe from the CS department, you might recognize D transpose D as the graph Laplacian. And solving linear systems in a graph Laplacian can be done very efficiently thanks to some pretty recent work by people in CS theory, also people here like Gary Miller at CMU. So you might be able to use some of these kind of very fast algorithms for solving linear systems and graph Laplacians on this Hessian, for example. In any case, this Hessian is still sparse, even if you didn't pay attention to its structure, so we can solve this quickly just kind of using generic sparse factorization methods. But there's a lot of different ways you would approach solving these linear systems. You wouldn't, just load this into MATLAB as a dense matrix. You'd think about it being sparse at the very least. And so in practical terms, we can solve a linear system in a Hessian of this form when D is this matrix close to linear time. So the interior point method is still very efficient for this penalty operator, the graph fuse lasso. Okay, so when we change from linear trend filtering over a line to graph-fused lasso, or even graph trend filtering, the story doesn't change. It looks like the interior point method is still the right thing to use. It has the same strengths as before, essentially, and all the other ones still have the same weaknesses. So that wasn't much different from our answer for linear trend filtering. But the story can change very suddenly with a tweak to the problem, and that's what we're going to see. So let's suppose that we actually changed the problem now, and we are interested in performing one of these kind of generalized lasso estimation problems, but we had regressors. We had predictor variables. Instead of just observing a sequence of observations, we actually observed a pair of observations and features. Okay, so let's change the Gaussian loss from being yi minus beta I summed up squared to yi minus the inner product of our feature vector xi with coefficients beta, and similarly for the logistic loss. So these are regression cases. This is like doing linear regression with a generalized lasso regularizer and logistic regression with a generalized lasso regularizer. Okay, so this could make sense in many ways. We didn't talk about much motivation for the regression case, but all of the kind of motivation we gave for the generalized lasso problems can be extended to the regression case. For example, suppose that I measure predictors over some graph, right? So let's say that actually one example is, let's suppose that I'm looking at some imaging problem where I have a scan of somebody's brain, and I'm trying to predict maybe something like the severity of their disease, or maybe even whether they have, let's say whether they have a disease or not, say Alzheimer's disease, from an MRI scan. So this would be my xi. It would be a whole image. And my yi would be 0 or 1, which is like, do they have Alzheimer's or not? So no disease or disease. So the number of components in each feature is the number of pixels in this image. So maybe trying to take MRI scans and predict Alzheimer's, but they have a very well-defined relationship, right? Let's say I take each pixel in the image as an individual feature. So my feature vector is the whole image. Well, these features are all related. So if I'm going to be assigning a coefficient to each feature or each pixel to predict the importance of, say, Alzheimer's disease, I may want to do something that picks out groups of pixels or groups of features in a spatially contiguous way. So that means if beta is high here, if it looks like this particular pixel in the image, which may correspond to a spot in the brain, is important in predicting Alzheimer's disease, then I may also want to say that it's likely for neighboring pixels to have a similar effect as well. And if these pixels are, say, important for the lack of Alzheimer's disease, predicting a 0, then maybe its neighbors should be as well. So if you think about it, xi transpose beta now, it's a linear combination of pixels times the coefficients we assign to those pixels. But the components of xi all have this graph structure, right? They all live on this grid. So we might enforce a graph-fused lasso penalty on beta that corresponds to the grid as well, right? We may regularize according to this penalty, right, for all I and j that are neighbors with respect to that graph. This is just saying what in a mathematical formula, what I said in words. If I have a pixel that, say, has a high value, maybe I should write as beta L minus beta J so that you don't confuse the two i's here. If this is pixel L and this is pixel J, then we want to encourage their values to be similar in order for the coefficients that we use to be kind of spatially contiguous. Okay, so that was an example of why we might care about the same type of regularization but with regressors. And so now we've made our problem class actually much bigger because we can have arbitrary measurements here for the regressors. Unfortunately, everything in the dual is more complicated now. Okay, so all of our nice picture with with the dual having structure and the interior point methods being tractable is pretty much ruined. Let's go through that and make sure we understand that. So the loss now is a function of xi transpose beta, right? Rather than just beta I, you can see I've replaced all instances of beta I with some inner product of a feature with beta. So I can actually think about it as being a function of the matrix x times beta, where x is my feature matrix. Each row is one of those xi's that you saw. So I can write the whole primal problem as some loss function, h of x beta, plus lambda times some matrix D times beta in the L1 norm. So before we had x equals the identity matrix. Now we have actually x being a dense matrix. Right? Or it at least has some structure that we're not going to claim we know, because it just comes from measurements. It doesn't come from design like D does. What is its dual? Its dual is not so simple anymore. Let's make sure we understand this dual derivation. So the primal problem is this one. Before, to derive its dual, we substituted z equals d beta. We formed the Lagrangian, minimized over beta and z, and then we got a nice clean dual, assuming we knew the conjugate of this loss function, which we're calling h now. That strategy is not going to work anymore. If you substitute in z for d beta, you can see that you're going to have, eventually you're going to have to derive a conjugate for h composed with x. That's going to be difficult to do, and it's going to depend on x inverse in some undesirable way. Right? And it'll actually become quite complicated. An equivalent way of deriving the dual to that, but it just ends up being a little bit cleaner with calculations, is to make two substitutions. So let's call this, don't remember what I called it. Oh, I don't have it here on the slides, but let's call it alpha, and let's call this z. Let's make the calculations a little cleaner for the Lagrangian. Right? Again, the high-level logic being, it's harder to take conjugates when you compose a function with another function. So let's make substitutions to make our life easier in minimizing the Lagrangian and forming the dual. So the primal problem then is equivalent to minimizing over beta, alpha, and z, h of alpha plus lambda times the L1 norm of z, subject to x beta equals alpha and d beta equals z. Right? So what's the Lagrangian here? The Lagrangian now is a function of beta, alpha, and z, my primal variables, and I get a dual variable, one for each constraint. And it looks like in the notes I called the dual variable corresponding to this one u and to this one v. And it's going to be given by taking the criterion function, right, and adding in u transpose d beta minus z, say, and v transpose x beta minus alpha. So depending on whether I got the signs the same as I had them originally here, I might get a different dual than this one, but it'll be equivalent, right? I could have written d beta minus z or z minus d beta, and they would have maybe given me equivalent duals up to a sign. So let's just collect terms. This is equal to, what are all my terms that involve alpha? I get h of alpha minus v transpose alpha. And what are all my terms that involve z? I get lambda z minus u transpose z. What are all my terms that involve beta? I get d transpose u plus x transpose v transpose beta. I want to minimize this over all the primal variables. beta, z, and alpha. That'll give me the dual function. Well, immediately we can see, right, if we minimize this over beta, this is going to either be minus infinity or 0. Right? So minimizing this over beta is going to give us an indicator function. Or equivalently, it's going to give us a constraint in the dual that says that d transpose u plus x transpose v has to be equal to 0. So the dual problem, we'll write it down, it's going to be to maximize over my dual variables, which are u and v. And we just know from this part, we're going to get a constraint that says that d transpose u plus x transpose v has to be equal to 0. And minimizing over this part, right, is again going to give me an indicator. It's going to give me either minus infinity or 0. And it's going to be 0 when u is in the L infinity ball of radius lambda. It's the same calculation we made before. Right? I can just think of this. I can pull out lambda. Right? This says lambda times the L1 norm of z minus u over z transpose, u over lambda transpose z. And now I can recognize this as the conjugate of the L1 norm. So I have another constraint that says that u has to have infinity norm less than or equal to lambda. Okay, and how about this part? Minimizing this over alpha is going to give me the negative conjugate of h at v, just by definition of the conjugate function. So that's my dual problem. And we can write it, instead of maximizing the negative conjugate, we can write it as minimizing the conjugate equivalently. So that's how we got that dual. So how does it look different than before? Let's make sure that we actually believe this is the same as it was before. What happens when X is the identity matrix? We should get the same dual as before. When X is the identity matrix, we get that d transpose u has to be equal to minus v. So this would become the conjugate of minus d transpose u. This equality we've taken care of just by saying, substituting in minus d transpose u from v, and we still have this box constraint on u. So it would look like minus the conjugate of minus d transpose u, subject to u being in the infinity ball of radius lambda. That's what we had before. Okay, so we're good in that sense. With an arbitrary X matrix, we can see now that the dual looks like this. If you look carefully, it's actually become much more complicated from the perspective of, say, applying an interior point method and proximal gradient, applying proximal gradient, both of them. And the reason is this equality constraint. So what is dual proximal gradient going to need? We can write all of these constraints as some non-smooth function. I don't know what you want to call it. Maybe call it, some function L. This looks like L of uv equal to 0, or less than or equal to 0, right? If we write this as our constraint. And so the prox is going to be the prox of that L function, right? So the prox, now we need to minimize prox of t given, say, u and v. It asks us to find the minimizer, say, over z and w of. This is just the regular formulation for the prox. Plus the non-smooth part. The non-smooth part is the indicator of this constraint happening, which I called L. But you can see that really just reduces to a constrained prox, right? Subject to d transpose, say, z plus x transpose w equals 0, and z having infinity norm less than or equal to lambda. So that's the proximal operator we need in the proximal gradient approach. Without this X matrix, that was very easy. We saw that just reduces to projection onto a ball, right, onto this ball, really onto a box, just the L infinity ball. With this X matrix, it becomes much more complicated. Think about it in the ZW space. This is the projection onto the intersection of a box with a plane. Right, so this determines some lower dimensional box. This determines a plane. And so the constraint set is really the intersection of these two things. So the prox operator is asking us to project uv, not onto just the box, but onto the intersection of the box with the plane. This is not a problem we can solve in closed form. In fact, this is, kind of a generic QP in some sense. So we're not going to have luck evaluating this prox efficiently. Okay, so that makes dual proximal gradient look much less desirable than before. How about the dual interior point methods? Right, those seem to do very well before. We'll see again, actually, the equality constraint kind of kills them. So if we're going to run an interior point method now on this dual problem, we're going to need to respect this equality constraint, right? So the barrier function is no harder. The barrier function, we just lift this into the criterion. And now we're having to run an equality constrained interior point method, which we know how to do because the intersteps will just become equality constrained Newton solves. But those intersteps are going to be very computationally difficult because of the form of this equality constraint. So they have to respect d transpose u plus x transpose v equals 0. So every Newton step now in the interior point method, instead of just adding the smoothed barrier function up into the criterion and solving a Newton step in that Hessian, remember we have to stack that Hessian with kind of the equality constraints so that our Newton steps will preserve this equality at every iteration. That was what we called the KKT matrix in earlier lectures. Okay, so the linear systems, let's just call this matrix A. So this looks like A, say A times uv equals 0. The linear systems we need to solve now look something like this. The Hessian times A transpose times A 0 times uv equals something. And so instead of just solving a linear system in the Hessian, we have to solve a much bigger linear system. Although this may still have structure, these two parts don't. Right? This A involves x, which is just some big dense matrix. So we're solving both a bigger linear system, and the structure has been killed. And so the Newton steps that underlie the interior point method are going to be much slower. Okay, so all of a sudden, by including an X matrix in the problem, the dual methods look, much less desirable. Questions about that? There's actually a further complication we should mention, which we just skipped over. This is the dual, right here. But what is the primal dual relationship? How do we get beta from u, or from uv? Even if the dual proximal gradient algorithm and the dual interior point method could be solved efficiently by some luck, right? If we didn't encounter these problems, we would still need to get the primal solution from the dual pair somehow in order to apply this in practice. We glossed over that. Now if we go back to the KKT conditions, right, we will see that the dual in primal variables are related by this equation. It's on the slides here. I think it's so to get beta from, say, u, we're going to have to solve this equation. Even if the loss was nice enough that we could express this gradient in a tractable form, you're going to see it still depends on inverting x in some way. So if this is squared error loss, if h is just equal to the Gaussian loss, so right in the case e.g. for Gaussian loss, where say h of its argument theta is equal to 1/2 say y minus theta squared. This is going to look like x transpose y minus x beta equals D transpose U. Or in other words, X transpose X beta equals Y minus D transpose U. So again, we can just kind of intuitively confirm this is the same as what we had before when X was identity, because in that case, remember, beta, if we looked back, was just equal to Y minus D transpose U. Now we need to solve a linear system to get beta. Oh, yeah, thank you. Okay, so even the primal dual relationship is complicated. And if you have a really big problem, you know, this even just getting the primal solution from the dual could be itself challenging. Okay, so everything has been messed up from our previous kind of perspective, once we include an X matrix. Do we have to go to the primal subgradient method, right? So the our kind of going through our list of algorithms, the dual ones were really appealing. Primal subgradient was super slow. And the primal proximal gradient we thought was just intractable. Now all of a sudden the dual ones look really bad. So does that mean we have to go to subgradient method? That's an option, right? We might have to solve one of these problems with the subgradient method. But there's another thing we can do with the primal proximal gradient method, which is an important thing to keep in mind in practice, which is that you can combine methods in some sense. And you're not really limited to any one algorithm. So here's an example of how you would combine them. So the primal subgradient method, just to recap, it still works, but it's just slow. There's not much more challenging, right? The subgradients now just look like this. Where gamma is a element of the subgradient of the one norm at d beta. So they didn't really become more challenging with the presence of an X matrix. We have kind of one more matrix multiplication now in computing the subgradient. But it still is applicable, and we could use it, but it's just slow. What about the primal proximal gradient? Well, right, reduces to solving this prox operator. Just as before. So by introducing an X matrix, nothing has changed. This is still a hard problem. It actually just looks like a much better option now, because let's think about solving this with the dual interior point method. Right, when we had no X matrix, that would be very silly, because we could have solved the problem directly with the dual interior point method. So there's no reason why we would ever want to kind of approximately evaluate the prox by treating it as an optimization problem. But with the introduction of an X matrix, the dual methods all of a sudden lost their appeal. They're much less tractable. Subgradient method didn't get any better, it's just as slow. So we could kind of combine strategies by using primal proximal gradient, and then at every proximal operation, we'll actually treat this as its own optimization problem and solve this with the dual interior point method. We've already seen that the dual interior point method can handle these with great speed, right? So the algorithm would proceed as follows. I mean, I just wrote it down here, basically. The prox operator, we just call a separate piece of code we wrote for this problem. and we just repeat that in the proximal gradient loop. Why is that maybe a desirable idea here? It's because we've completely freed ourselves of linear systems in X. Right? So if X is this big dense matrix of predictors that we measured, we don't know anything about its structure, then by applying proximal gradient, you can think about it as taking the Hessian, which involved X, and transforming it to a sequence of problems whose Hessians were diagonal, or really the identity. Right? Proximal gradient makes a quadratic approximation, but it doesn't actually use the Hessian. It just uses an identity, a multiple identity for the Hessian. So that takes care of X. Once we've made the kind of the proximal quadratic approximation, there's no more X. This problem we know how to solve very efficiently. And so we'll just now look at this problem from the perspective that we had previously, which is let's solve it with the dual interior point method. So an example of how you might combine proximal gradient with another method to solve the prox efficiently. And so this ends up among the methods that just we've covered so far in class for, say, a regression problem where D is structured but X is not. This is the best approach of the ones we've seen. Questions about that? So one caveat I gave when when we learned the proximal gradient method was that I said if you have to approximately evaluate the prox, then you could encounter problems unless you do it to high accuracy. If you remember, if you go back to that lecture, there's a slide that says what happens if we can't evaluate the prox, and we actually treat it as a separate optimization problem. Then both kind of empirical analysis, and also there's a few papers on this topic, show that if you're going to do that, you better evaluate the prox to high accuracy. Otherwise, the errors accumulated in just approximately evaluating the prox can mess up the proximal gradient approach. So that's why we chose, it's in part why we chose to use an interior point method here, because we know that this is going to give us a very accurate solution to this prox. We're only evaluating approximately. With the interior point method, we're going to get very close to the exact solution. Questions? Okay, let's take a few minute break, and we'll see the last couple cases for the generalized lasso. Diffuse lasso with regressors, but I don't think it's really worth going through in that much detail. I just wanted to show you that I was not making up that story about MRI imaging, that people have done this kind of thing. So this is a paper you can look at if you're curious. I don't know these authors, but it's a nice paper on using diffuse lasso over MRI images to predict the onset of Alzheimer's disease. And this is another example of a kind of a regression problem you can set up with these types of penalties. And in this case, actually, the algorithm that was used was just the one I was describing. It's precisely use proximal gradient and then do something clever with the... To get rid of X, use proximal gradient to get rid of the X matrix, then do something clever with the prox. And that do something clever is actually what we're going to talk about right now. In this case, what they used was something a little bit different, but they still used a proximal operation to get rid of X. So let's go to a very special case of the things we've been talking about, which is we talked about the diffuse lasso over a graph with regressors. What happens if the graph is just the chain? So really we're doing a 1D diffuse lasso. So we're just penalizing, right, the difference between adjacent nodes when we arrange them on a line, and that's our graph. And so it's just like back to the 1D diffuse lasso. You could do what I described before, do proximal gradient to get rid of the X matrix, solve each prox step by going to the dual and running interior point method. But in this case, another kind of interesting thing to keep in mind is that there is a very specialized algorithm for solving the prox that does not require you to go to the dual. So this graph has enough structure that you can actually solve this proximal operator with a very specialized algorithm that is not iterative. It's not like an interior point method. It's a direct algorithm that you can do with dynamic programming, for example, because of the linear structure here. And this is not only true of the chain graph, it's also true of the complete graph. It's true of another few graph structures. So the point here is that for certain graph structures, if you're only interested in the chain or, say, the complete graph or other kind of very structured graphs, you might spend a few minutes looking up the literature as to whether or not you can solve the prox in a more efficient manner than an interior point method. And for this prox, the answer ends up being dynamic programming. Actually, in some sense, this prox goes all the way back to Bellman in the 1960s. But there are more recent kind of formulations of dynamic programming or other kind of related methods for solving this, and they're all linear time, and they're direct, so they're very fast. Okay, so if we have the fused lasso on a chain, or the one diffuse lasso with an X matrix, then we don't need to actually do anything more involved with the dual, with the prox, where we go to the dual and apply interior point method. We can hopefully just download some fast code from these authors and run that instead. Okay, so I just wanted to point out this case as an example of when you should kind of think about whether there are specific structures in your problem that can be directly solved, and you can try to find maybe some literature on that rather than running a generic algorithm like an interior point method. This is just an empirical evaluation that I did to show you really how fast this proximal operator is. So it's order n, right? That's what I claimed here. But it's order n with a very small constant. And you'll see how small that constant is just by comparing that proximal operator in blue to a banded matrix solve. So this, on the x-axis, is the problem size, n. On the y-axis is the amount of time it took me to solve either the prox with the dynamic programming algorithm that I mentioned, or to perform a single banded matrix solve, where that would be one iteration of an interior point method. So I'm comparing one iteration of an interior point method. Remember, we need many iterations of those to solve the prox if we're running interior point method on the dual, versus just one evaluation of that prox directly with dynamic programming. Even compared to one iteration of the interior point method, the prox given by dynamic programming is much faster. They're both linear. They both scale with n. But you can see the constant scaling is actually more favorable towards the dynamic programming. Again, just to be clear, we're comparing one iteration of primal dual interior point method, say, with just one run of dynamic programming. So it's really fast. There's no reason why you should go to the interior point method, especially after you run a bit of preliminary analysis like this. It also gives you the prox directly with no worries about how accurate you are. So in this case, we would do proximal gradient, and we just would evaluate this prox directly with some analysis code we found that ran quickly. Okay, so I'll just quickly go over this. It's interesting, even furthermore, to compare how the interior point method does versus for solving this prox versus the dynamic programming algorithm if we just look at those directly. Even though we know that it should be faster, it's interesting to see kind of their convergence behaviors as lambda varies. Lambda is going to be the regularization parameter we had in the generalized Lasso problem. It determines the strength of regularization, right? So in this example, bigger lambda meant fewer linear pieces. I just want to point out to you where it appears. Right? It appears right here. It controls the strength of the regularization term. And it appears in the dual by controlling the radius of the dual infinity norm ball. So just very quickly, I wanted to point out that if we solved a sequence of problems across a grid of lambdas, suppose we didn't know what kind of level of regularization we wanted in the first place, we would find that the primal approach, which solves this prox directly, It does quite well when lambda is large, and it has increasingly more trouble when lambda gets small. So in this case, I'm solving a logistic problem without predictors, and I'm using primal proximal gradient with the fast prox given by this dynamic programming algorithm across a grid of lambdas. So x-axis is the lambda value. The y-axis is the number of prox operations I needed to get an accuracy of a certain amount, let's say 10 to the minus 5. 10 to the minus 5 away from optimality. And I capped it at 1,000. So that's why you can see it flattens out here. I just let the algorithm quit after 1,000. So as lambda gets smaller, the problem gets harder. We need more prox evaluations to get an accurate solution. That's what we see. The difference between the red and the black is not so important. That's cold versus warm starts. So you can kind of ignore that for now. In the dual, we can see that as lambda gets smaller, ignoring these trivial cases, because in these cases, lambda is so large that we don't really have to do anything. We've initialized the algorithm properly. Because remember, the dual is to solve a problem where u lies inside a box of radius lambda. When lambda is large enough, the initial point will lie inside that ball, and so the algorithm kind of runs very quickly. The general trend is not as definitive as it is in the primal, but we can see that it does get easier as lambda gets smaller, right? We go from needing maybe a little over 100 iterations of the interior point method, this in terms of the number of Newton iterations, to about 80 or so as lambda gets smaller. Okay, and if we compare the two, then these aren't on the same scale, but let's think about drawing a line at about 100, say. That would be up here. If we use the primal approach and we solve the prox with dynamic programming, then the number of iterations required, the number of proxies required to converge is very small, for lambda about 0.01 or 0.1 or higher. And then it looks like the Newton method, or the dual method, might start winning, because at that point the primal approach needs over maybe 100 prox iterations, but the dual approach looks like it's actually needing less and less Newton steps to converge. So the summary is that the primal approach is better for large lambda, the dual approach is better for small lambda, right? If we had to look at these two plots and figure out what to use in what regime. So very quickly, I wanted to just give you some intuition for why that is the case. If you look at the primal and dual problems, you'll see that in rough terms, the sparsity pattern is reversed between the two. So in the primal, when lambda is large, there are many components of these differences, d times beta, that are 0 by construction. As I make lambda larger, many differences are 0. Whereas for large lambda, in the dual, there are many components that are strictly inside the box. Right? They're strictly between minus lambda and lambda. For small lambda, many components are non-zero by construction. We're going to have d beta being kind of denser and denser as lambda gets smaller and smaller. But in the dual, as lambda gets smaller and smaller, the box is getting tighter and tighter. More components of the dual solution are going to lie in the boundary. So there'll be less in the interior. In a very kind of rough sense, when many of these differences are 0, there are fewer effective parameters in the primal. Right, so an iterative algorithm would set many of them to 0, and then it probably wouldn't touch them from then on, and it would just iterate over the remaining non-zero ones in some rough sense until convergence. So effectively, it's solving an optimization problem in a lower dimension. In the dual, it's the similar story, except for now the important notion is whether it's on the boundary of the box or not. If there are many dual coordinates that are on the boundary, then again, maybe our some approach that is going to put these on the boundary is just going to put a bunch on the boundary, and it would not touch them, and it would iterate on the interior until it had the right solution. So if many are on the boundary, there are fewer effective parameters when we're going to solve the dual. That was a very kind of hand-wavy explanation, but there's some kind of more refined analysis you can show that says this is actually true in terms of convergence rates. So the take-home point is that large lambda is easier for primal algorithms, and small lambda is easier for dual algorithms. because they have kind of the opposite notion of sparsity. So that's why we saw that phenomenon. And that's something to keep in mind in general if you're going to be looking at, a regularized problem in the primal or the dual. You'll get kind of a similar phenomenon. In the previous example, right, we saw that the dual interior point method, it looks like it starts winning about lambda equals 0.1. It uses fewer Newton counts than the primal would use prox evaluations. The solution at lambda equals 0.1 is this red line here. So you can see that's just crazily under-regularized in terms of a valid solution. I don't know how well you can see here, but the true data generating probability is this black dotted line. We're observing binomial or Bernoulli observations around it. We're trying to solve kind of a regularized estimation problem to recover this piecewise constant probability. When lambda is 0.1, this is the solution we get in red. That's solved to high accuracy. So that's so under-regularized that the dual starts winning in a regime where it's not interesting, basically. For all practical purposes, or all statistical purposes, the dual does do better for small lambda, but lambda is so small it's not statistically interesting. When lambda is 15, if you go back to lambda equals 15, the primal approach completely dominates the dual approach, and you can see that gives us the solution in blue here, which is pretty close to the data generating probability mechanism. Okay, so all these considerations, maybe are important things to keep in mind if you're going to solve a regularized problem in the primal and in the dual. Okay, any questions about that? I'm going to go to our last example, which is a big, dense D matrix. Okay, so we've seen how to, examples of how we might approach solving some of these problems with different structures on D and different structures on maybe the regressors, or the presence of regressors or no regressors. In our last problem, let's just consider a very big, dense matrix D. For whatever reason, and we gave some motivation at the start, had to do with the equality-constrained Lasso problem and also other kind of analysis problems. Suppose we want to solve a problem that was regularizing according to D beta, but D was just big and dense. So the primal proximal approach, again, it's intractable. This is a very hard thing to solve. Doesn't really make sense to go to the dual and try to solve this by an interior point method because D is dense and those will be expensive. Right, so both the primal prox and the dual interior point method have very costly Newton steps. Or sorry, the dual interior point method has very costly Newton steps because D is dense. We're solving linear systems in D. We know that solving a linear system in a dense matrix is much more expensive than solving one in a structured matrix. Dual proximal gradient now is starting to look pretty good. It's an example where it looks kind of poor in all of the other problem instances. In this case, it actually looks pretty good. Right? Why? It's because if you remember what the dual looked like, it was projecting something that had to do with the gradient of our smooth part onto the box. Right, so the gradient of this is just going to be given by minus d times the gradient of f star evaluated at minus d transpose u. That's possible to calculate even when d is dense, just requires a matrix multiplication. And the steps of proximal gradient would take where we are, and it would subtract off t times the gradient. So it would really, add t times this quantity, and it would project this onto a box. That's easy to do, nothing to do with solving linear systems in D. D only appears in the calculation of the gradient, so its steps are quite efficient. Right, so compared to the others, that may start looking quite favorable now, whereas before it always looked quite unfavorable. It's still going to suffer from the issue of needing meta iterations to converge to high accuracy, but it may be our only approach that's really feasible in this case. or maybe the most efficient approach in this case. Very last twist on this is, let's suppose D was dense, but it was also so big that you couldn't fit it into memory. So I actually couldn't even fit D into memory to make this matrix multiplication down here. Well, now the primal subgradient method is starting to look like, the winner. Because if you remember from our calculation of the subgradient, all we need in order to evaluate the subgradient are the rows of D that correspond to active elements of D beta. So non-zero elements of D beta. So the subgradient, right, of the primal criterion is just the gradient of the loss plus lambda times the subgradient of the L1 norm of D beta. Now, if D is so big we couldn't fit it into memory, then we might keep a list of which components of D beta were non-zero at each step. We only load those rows into memory. We take their product with beta, look at the sign, and add up the rows correspondingly. That gives us a subgradient. And then we could kick those back out of memory and make the subgradient update and continue. So for such a big problem we can't fit into memory, it looks like subgradient method may be the best approach. An even better approach would probably be to use something stochastic here. So to stochastically evaluate the gradient, and possibly even this part, by just choosing a random sample of observations and constraints to look at each step, and then updating the gradient and subgradient according to those. And this is the kind of strategy people actually take in practice to solve really massive problems. Right? The algorithms get simpler and simpler. They go from fancy interior point methods maybe to simpler methods like subgradient method, but with stochastic tricks or active set tricks like this one, because that's all we can do when these matrices are so large that we can't have them in memory. Okay, so I've tried to go through and just give you a sense for the idea that no one algorithm dominates the other. We've actually seen situations in which each algorithm may appear as the most favorable, and even combinations of algorithms may appear most favorable. So here's the takeaway points. I hope that you are able to remember this slide in the future, because I tried to use the generalized Lasso kind of framework as an example of where we might go through this logic, but really these ideas are more general. So the first thing we saw was that there's no single best method. The performance is going to depend greatly on the structure of the penalty or the regularizer that you're using. If you're going to the dual, it depends on the conjugate of the loss. Is that possible to derive? Depends on what accuracy level you want. Do you want an accurate solution or not? And it depends on the sought regularization level. It depends on lambda. We even saw that different levels of lambda, different methods drive. A very important thing to remember is that duality is your friend. So dual approaches, they're often going to be complementary to what you can do in the primal. So I said this last lecture, but I'll say it again. You should always derive the dual, even if you're confident you know how to solve the problem in the primal. It's not going to hurt. Just derive the dual and see what you can get out of it. What does the dual do in rough terms? It takes linear transformations in one part of the criterion function and enables you to move it into the other. So if there's a linear transformation in the regularizer, and the regularizer is non-smooth, taking the dual moves that to the criterion. And so now the non-smooth part in the dual becomes simpler. That's what we saw. In this calculation, this is what we saw. The non-smooth part moved from the linear transformation moved from the non-smooth regularizer into the smooth criterion function when we went to the dual. And the regularizer was kind of simplified. It was freed of that linear transformation. And vice versa as well. If you have a linear transformation in the say the smooth criterion function, you could move it into the regularizer by going to the dual. So that's something to keep in mind when a linear transformation like that is complicating your understanding of the regularizer. The dual also offers success in different regularization regimes. So it's going to succeed if you're solving regularized problems at different levels of the regularization parameter because of that high-level reasoning I gave before. Regressors complicate duality. This is, again, it's a persistent point. It's not to do just with the generalized Lasso. This is going to be kind of always true. For that same reason, regressors are a linear transformation in the smooth part of the loss, and the dual moves them to the non-smooth part of the loss. You have a loss plus regularizer. So that's going to complicate the nature of, or the role played by the non-smooth part in the dual. One way to get around that is to use proximal gradient in the primal, and that'll completely relieve yourself of, dealing with problems involving x, because you take in a sense, you're taking the primal problem and you're approximating the smooth part by a quadratic that does not involve x at all. Right, so that's a generic strategy to try to reduce the problem with regressors to one without regressors. Another important takeaway point is to try to recognize easy subproblems. So if there's something that's a specialized case or a special case of your problem, and you can recognize that's an easy subproblem to solve, you can often design your algorithm around it. And that's what we saw with this case of the one diffuse lasso, where we recognized that prox was actually really quite simple. It had to do with some kind of dynamic programming approach over a line. And we designed our algorithm around that. We decided to use proximal gradient because the prox was so efficient. This is a point that's also going to be important when we talk about ADMM coming up. So if we can recognize an easy subproblem, we're going to want to kind of design the algorithm around that. And the last one is an important point, although it's not what we've stressed at all in this class, because this would be maybe taught in an advanced optimization course or one that has to do with kind of more systems type work, is that at scale, memory limitations become kind of very serious, and so active set and stochastic methods may be the only option you have. If you have a really, really large problem, the methods that deal with active sets and evaluate gradients and subgradients stochastically, they will still work, and they may be your only option. Any questions about these principles or about the examples we saw? Okay. You may be, just completely burnt out from the generalized lasso problem, but when we go to the advanced methods like ADMM and other advanced methods, it might be an exercise for you to play in your mind, or say when you have time, to go through them and see which of them can be applied to these problem instances and where they would strive and fail. Because a lot of them can also be applied to these problems, and they may even improve on the methods we learned. So that's the point of this slide. Your toolbox is only going to get bigger as we go forward. ADMM, proximal and projective Newton, path following methods, all of these are viable options as well, and they may even be a better option than the ones that we learned today, depending on the situation. And one other kind of point to keep in mind is that when you're seeking to solve a problem in your research, you don't have to design the perfect algorithm. You don't have to choose the one that works absolutely the best and go through the most exhaustive analysis and spend the majority of your time comparing 10 methods. You have to just find one that works well. Right? So if you end up choosing an interior point method and ADMM has a slight advantage, it's not the end of the world. But if you ended up choosing the interior point method and it worked terribly and you didn't consider anything else, then that would be a bigger deal. Right? So just finding one that works well is really the point. Finding the optimal algorithm is, may be interesting, but it may also be very hard to go through exhaustively all the methods you learned. Tools like CVX and TFOX, we use CVX on the very first homework assignment. TFOX is similar, although I'd say it's a little faster and more specialized. There are also important things to kind of have in the back of your head when you don't care about performance at all and you just want to do some prototyping. These tools, if you recall, those solve generic convex problems as long as you can kind of formulate them in the right language. So if you want to do some prototyping, you don't want to expend a lot of programming effort, you don't want to compare 5 methods, you just want to see whether the problem you wrote down makes sense, you can use CVX or even TFOX, which are both freely available disciplined convex programming packages to get an answer. So I want to spend the last 5 minutes on implementation because this is something that is really not focused on at all when we teach optimization. It's maybe more of almost an engineering concern, but I wanted to go through it. And we didn't cover the midterm topics today. If there's a lot of open questions, we'll cover them next time. But please look at them, say, between now and Monday, the solutions. And if you have ones that you can't figure out, we can do them Monday. Otherwise, I'd be happy if you just figure them out from looking at the solutions. So implementation. Like I said, not a focus in optimization courses. Typically, it's thought of more of maybe as an engineering pursuit. But I think implementation skills are really undervalued. So I wanted to spend just a few minutes talking about some ideas that you may keep in your mind if you're talking about implementing an algorithm like the ones we talked about today for a problem with the idea of performance. You want to maybe provide code that you're going to make public or something for people to use to solve your favorite problem. So what are some considerations? Speed. There's no reason we have to explain that one. That one's, right, it's obvious. Robustness. This one is a little bit less, it's focused on less certainly than speed. Robustness refers to the stability of your implementation across various cases. Right? So let's suppose we're writing an algorithm to solve the fuse lasso over graphs, and the graphs can have edge weights. So we may have an algorithm that works really well when the edge weights are all kind of close to the same. They're close to uniform. But robustness refers to the idea, how well does it perform if some of the edge weights are huge and some are tiny? If the algorithm is not robust, then it might fail in that case, and it might not be something we think about when we make the code public for other people to use, but certainly something that we should pay attention to, because you don't really know ahead of time what the kind of common problem cases are going to be for people when they're applying your software. It could also have to do with the regularization parameter lambda. Maybe our algorithm only works well for lambda in some small range. How robust is it to the choice of regularization parameter? This is a very kind of important concern, especially if we're going to be making our implementation public. Simplicity and portability, I'd say, are definitely by far less of a focus than robustness, which is in turn less of a focus than speed. Typically, it goes speed is the most important thing we think about first, and then robustness, and then we maybe even forget to think about simplicity and portability. Although I would say these are all extremely important. Simplicity has to do with the idea of, let's suppose I write my favorite algorithm. It takes 10,000 lines of code, and I'm not kidding. There are some implementations of algorithms, say, for these problems that have on the order of tens of thousands of lines of code. That may run fast, but what happens when you find a bug? And what's going to happen if you decided you want to pass on to your friend or your colleague? What happens if you didn't think about it for a few years and then wanted to extend it? All of these things point to the idea that simplicity of implementation is actually a really undervalued property. Portability is the idea of being able to take your code and use it either in different problems or use it even in different programming languages. Is it able to port to MATLAB if you wrote it in R? Is it able to port to Python? These are all important considerations. So some tips, and these are rules of thumb. You may disagree with me, but these are certainly things I think that are worth mentioning. A constant factor speedup is probably not worth a more complicated implementation. So if you have one implementation that runs in a certain empirical amount of time, and then you make it much more complicated, and it gives you a 2-time speedup or a 3-time speedup, it's honestly probably not worth it. We don't typically worry about orders of magnitude speedups that are, they're the same rate of convergence, but you get like a 2-time improvement. It may be nice, but I don't think it's generically worth sacrificing simplicity for that. It may be worth a loss of simplicity if you are able to make a more complicated implementation that can converge to a higher degree of accuracy quickly. Right? If you have an 1 over k algorithm that's simple, but your 1 over k squared, or maybe your linear algorithm that converges like c to the k is much more complicated, that, I think, you can argue for that might be worth it. It obviously depends on the case, but something to keep in mind. I think writing code in a lower level language like C or C++ is a good thing to practice, especially when you're working on portability. Right? Almost every language can take something written in C and wrap and be wrapped around it, like R and MATLAB and Python and Julia. All these languages, they can take C code, and you can write easy wrappers around them. And my last tip would be, do not re-implement standard routines. Something I see people doing all the time, and I'm guilty of it myself as well. You don't have to reinvent the wheel every time you solve an optimization problem. That's especially true for numerical linear algebra. So when I was a graduate student, I spent way too long time implementing updates for QWERTY compositions. And when I look back at it, I kind of wish somebody had told me, don't do that. There's LawPack, there's LimPack, there's tons of good open source free resources for numerical linear algebra. Re-implementing these things on your own makes it prone to bugs. It makes it much harder to port to other languages. It's just not worth your time. So you should always be looking at where you can find kind of high-quality implementations of standard routines. So maybe that'll save one of you from spending so much time on implementing a QWERTY composition. So that was really it. We kind of went through this stuff quickly, but I hope that it made an impression on you that all these practical considerations are important as well. Next time we're going to get back to kind of higher level algorithm stuff, and we'll learn some advanced methods.